Hi, this is Mrs. Westmoreland, and this is a lecture on the dissociation of strong and weak acids and bases, as well as conjugate acid-base pairs. So, strong acids, by the chemistry definition, dissociate completely in water, which means they are 100% split into ions in aqueous solution. And there are 6 strong acids to memorize, which are listed there. All other acids are considered to be weak. And the equation for dissociation shows how those acids split up into ions. So a simplified version of the dissociation equation omits water from the equation and demonstrates what we call the Arrhenius definition of acids, which simply says that acids give up hydrogen ion when they are in aqueous solution. So we can see the nitric acid in the example. The arrow goes in one direction because it's strong, and we're showing that it goes completely to the products, and it splits up into the H plus ion and the NO3 ion with their charges. A truer representation of what really goes on in the solution shows water as a reactant and demonstrates more what's called the Bronsted-Lowry definition, in that we're talking about acids being proton donors. So a proton is simply an H plus ion, so there's not a whole lot of difference between the Bronsted-Lowry and the Arrhenius definition. But Bronsted-Lowry really talks about donating, which means giving that H plus to something else. And in this case, the acid is giving the H plus to the water. So the nitric acid still dissociates into the H plus and the NO3 It's just that the H plus is donated or given to the water, forming the hydronium ion as the product. For weak acids, the difference is that the arrow is drawn in 2 directions because for those the system is at equilibrium. For every molecule that breaks into ions, the ions are going to form back together into a molecule, and really at equilibrium only a small amount is going to be in the ion form. So you can see here nitrous acid, not on our list of strong acids, in the simplified version or in the version that includes water as a reactant. There are a category of weak acids that are used in organic chemistry that you might see on the AP exam. They're known as carboxylic acids. They end in COOH in their chemical formula. Organic chemistry sort of writes the order of the elements a little bit differently. And it's the H at the end of the COOH that breaks off and becomes the H plus ion. So there's an example both of the simplified version and the version with water of this acid that's known as methanoic acid. And you can see it's splitting up into the H plus, and then what remains of the molecule is the anion, both with water included and not. So strong bases also, like strong acids, dissociate completely in water. And strong bases are the group 1 metals as well as the group 2 metals that are soluble with hydroxide. And really mostly we're talking about strontium and barium being the soluble ones, the ones at the bottom of the column 2. So when we look at equations for dissociation of these strong bases, we're really looking at the Arrhenius definition of bases, where bases are going to give up hydroxide. No water is included because there isn't any interaction between the hydroxide ion really and the water other than being surrounded by the shells of hydration. There's no new ion or new species that's formed when they dissociate. So this is more like just ionic compounds dissociating. So we can see sodium hydroxide splitting up into sodium plus 1 ion and hydroxide minus 1 ion. Calcium hydroxide splitting up completely into calcium 2 plus ion. And then 2 moles of hydroxide ion. All other bases are weak. So if they include hydroxide in their chemical formula, then no water is needed in the dissociation equation. The only difference would be we would draw the arrow in 2 directions, like the one here for copper 1 hydroxide. But we have to have the Bronsted-Lowry definition for bases really because of a specific group of bases that don't have hydroxide in their chemical formula. And for that one, you really must include water in the dissociation equation. Ammonia would be sort of the most famous base. It's got all the properties of bases, turns litmus paper blue and feels slippery and conducts electricity and has a high pH. And so the Bronsted-Lowry definition of bases says that bases are the proton acceptors. So we need the water in this dissociation equation to be the proton donor, to act as the acid. So the water, we know, auto-ionizes, splits up to a small extent into H plus and OH minus. And so when ammonia is in the aqueous solution with that water, the H plus of the water is very attracted to the negative end of the ammonia molecule and kind of rides piggyback on that. And so the water is, in this case, the proton donor, and the ammonia, the base, is the proton acceptor, and we form, in that case, ammonium ion, and hydroxide ion is left over from what split up of the water. So even though hydroxide is not part of the chemical formula of the ammonia, hydroxide is still formed in the aqueous solution because of its interaction with water. So the final thing to talk about here with equations for dissociation is identifying what are known as the conjugate acid-base pairs. So here's a generalized equation for the dissociation of a weak acid, where HA, where A is just any anion, is dissociating in water to form hydronium and the A minus anion. So the conjugate base is everything that remains of the acid molecule after a proton is lost. So it's the anion. And the conjugate acid is formed when the proton is transferred to the base. So since in this dissociation water was acting as a base, the conjugate acid is the hydronium ion that is formed when that base accepts the proton. So we will be looking for conjugate acid-base pairs in these dissociations where we have two substances that are related to each other by the donating and accepting of a single proton. So for the example above, the pairs would be the acid and its conjugate base in the product side, the A minus, and the base, which in this case water was acting as the proton acceptor, so it's the base, and hydronium, which is what's formed when it picks up the proton. Thanks for listening. See you in class.